Okay, so, well, yes, but I just wanted to start asking, well, because in 2006, you and your colleague, George Smoot, were awarded the Nobel Prize in Physics for, and I quote, your discovery of the black body form and anisotropy of the cosmic microwave background radiation. And I just wanted to know if you could maybe try and explain what this means, what this implies for maybe an undergraduate level, so the attendees of this Congress may understand what this means.
Yes, so when we discovered in 1929 that the distant galaxies are going away from us very fast, and we understood that the universe is expanding, people realized right away that maybe it was possible that it was very hot when it was young. And then in the 1940s, it was predicted that the cosmic microwave background radiation should exist. It is the heat of the early universe. And then nobody went to look to see if it was true. In 1965, it was discovered. And then our measurement was to confirm the details and see if it really is the remnant of the Big Bang. So the answer is yes. The black body form means it's a spectrum without a color. It's just only got a temperature. So if you can measure the temperature, then you know the exact amount of radiation at all frequencies and all wavelengths. And this little sketch on the board behind you shows the idea. So there's a very simple formula that says how bright it should be at every wavelength. And so that was our number one question. Is it really the remains of the Big Bang? And the answer was yes, extremely precisely, within 50 parts per million, which was an extraordinary result. And then the second question is, well, is it equally bright in all directions? And the answer is almost, but not exactly. It should be almost exactly the same in every direction if it really is something from the whole universe. And if it were perfectly the same in every direction, then we would not exist. Sure. Because there would be nothing for gravity to work on to stop the expansion. So it was suggested that there should be some sign of density variations in the early universe so that gravity could stop the expansion locally. And so there should be spots, so hot and cold spots in the microwave radiation from that early times. And so that's what we found. We made a map and said, well, it's very, very nearly the same. It's only different by about 1 part in 100,000 from place to place. So that was just enough to match the predictions and calculations of where the galaxies are. And so it was a tremendous triumph. And when we started the idea and proposed the mission in 1974, we had no prediction. Nobody had any idea what we should see. So then we were so pleased that it was there. And following that, 2 more satellites were built by one by NASA and one by European Space Agency to get all the details. So now we say, yes, for sure, it is the remnant of the Big Bang. We know the initial conditions of the expanding universe. So Stephen Hawking said that those spots that we saw were the most important scientific discovery of the century, if not of all time. And so why was that important? Well, several things. Number one, we wouldn't be here without those spots. Number two, most of the spots come from cosmic dark matter, which we deduce but cannot see. And number three, this pattern of the spots is influenced by cosmic dark energy, which you also deduce but cannot see. And that may be number four, if we ever understand what makes the spots, we'll get some idea about quantum gravity. And we now have a story about cosmic inflation that tells us about the expanding universe and why it's expanding. And so as it happens with more detail about those spots, we can confirm that prediction also. So we've done a lot of things with this subject, which we basically started.
And how come that from 1929 that you say this was first like theorized until nobody looked at it really?
Well, and when it was first predicted in 1940 something, it was too hard to measure.
Okay.
We didn't have the technology yet. Although if somebody knew there was a Nobel Prize for it, maybe they would have tried harder. But nobody thought we could do it. It was just at the end of the war. And we had just begun to develop the technology with the radar and other microwave equipment. So it would have been very difficult right then.
Okay, sure.
Yeah, when it was finally discovered in 1965, it was because we had new technology. And we were beginning to try to communicate with satellites. So people at Bell Telephone Laboratories had built some equipment for that purpose.
And regarding the Nobel Prize that you just mentioned that you won, I just wanted to ask you, how did you feel about that? And in particular, like, how did you receive the news? Like, were you expecting the call, or were you like doing the dishes or something? Or?
Yeah, so it comes where we live in Washington, D.C. area. It comes at 6 o'clock in the morning.
Okay.
So I'm lying in bed, and the telephone rings, and there's a telephone by the bed. So I say hello, and they say they're calling, and so I say that's very nice. So because my mother was old and sick, and so maybe it's a problem with maybe my mother is sick, and anyway, so I suddenly knew my whole world is about to change. So I'm now going to be a famous person. And so my hope at the time was, let me continue to do what I already know how to do, which is to talk about science. And I was already working on the James Webb Space Telescope at that time. So this will give me another way to explain why the great new telescope is important. So we'll talk about that. So I kept on working on the telescope.
Okay, well, sorry?
Yeah, so of course, then you go off to Stockholm and you have parties and speeches for 10 days.
Oh, good.
And you get to have dinner at the king's house at the castle. And anyway, it's a very spectacular process to receive the prize.
And regarding your field, the field that you work on, which is, well, cosmology, right? You're experimental cosmologist in particular, but regarding cosmology in general, when you were an undergrad student, were you like always driven towards cosmology, or you thought you maybe would do something else?
No, I wasn't. When I was not an undergraduate, just a freshman in college when the cosmic background radiation was discovered. So I thought, well, that's not so surprising. I had read about it in a popular book by George Gamow, that there should be such radiation. Okay, well, that's not that exciting because we should know that already. That's what I thought. So, however, I was excited about relativity and quantum mechanics. I thought that was the most fascinating and mysterious thing there was to think about. And so in college and graduate school, I thought I would be a theoretical physicist. I want to know the mysteries of everything. And so then I was looking for a thesis project. Well, should I work on that? And they said, are you rich? There are no jobs. So you can do this if you're independently wealthy. Yeah. No, I'm not. So find a thesis project, somebody who has something to go build or measure. So let's go measure the cosmic microwave background radiation. So that was 1970. I'm looking for a thesis project. So we got started. And then what happened? Well, we built a project, two of them, one on the ground to try to measure the radiation, and a balloon payload to go up 40 kilometers into upper atmosphere to look for the cosmic radiation. And then incidentally, John Beckman also worked on this very much. So I didn't know about his work at the time. I just knew this was a really interesting thing to try. So our project did not work correctly the first time. So I got to write a thesis about a failed project. And got a job for NASA to become a radio astronomer in New York City.
Oh, that's cool.
So, so I'm sitting there in New York City trying to become a radio astronomer, and NASA said that summer, well, we want proposals for new satellites. I said, boss, my thesis project failed, but we should try it in outer space. So that became the Cosmic Background Explorer satellite, the COBE satellite that won the Nobel Prize for us.
So at the end of the day, it was kind of by chance, maybe, because...
Very much, it feels very random.
Because you had like this other whole idea in mind, but, well, it's always because of the money, right? So
yeah, so, respond to opportunity. Our grandsons play soccer, they football, and they run back and forth in a very random-looking way. And I have the feeling that life is like that. And so if you get the ball and you kick it in some direction, maybe it'll work. And so that happened to me.
That's a very nice analogy, actually. So regarding something that you said before as well, which was that you served as the senior project scientist for the James Webb Space Telescope, I think that, well, when I first read that, I thought, oh, that this looks like a cool, important job, but honestly, I don't really have any idea what that could mean. So I just wanted to ask you, perhaps, if you could tell us what your responsibilities were in this position and how you contributed to work in, well, what is now the state-of-the-art of space telescopes, and how do you feel about your work in there?
Yeah, so number one job is to work with an engineering team to say, well, what could we build?
Sure.
And because the scientists had already written a little book that said they want this telescope. Okay, well, how do you build that? So I like to invent ways to think about measuring things. I've been fascinated with telescopes since I was a child. So, okay, talk to scientists and to engineers to make a way. So help invent the new technologies, encourage the people, show them how important it is. And so I did that a lot with the engineering team. Also, I worked with international teams of scientists to say, okay, what exactly are we going to build? And especially with the teams of scientists that built the instruments. So the telescope has, of course, the big mirror and the sunshade to keep it cold and all the electronics and so forth to make a telescope work in space. Then we have to have cameras and spectrometers. So then we had to find a way to get all four of those instruments. So one's from Canada, one's from Europe, one's from the United States, and one is a joint project of Canada, of Europe and the United States. So we had to find a way to organize all those things and get scientists to produce those instruments. So a lot of talking, a lot of going to meetings, and lots of saying, well, this would be really good if we could do this, and then find a way to do this. So some of it's science and a lot of it's talk.
Yeah, sure, but it sure seems as well like a very creative process, right? Because
it is. It's a very creative process.
Come up with a lot of ideas.
You have to find a way to do what's never been done before.
Yeah, sure.
So you can observe something that's never been seen before.
You can Google it because it doesn't exist.
Yes, it does not exist. You cannot find it. But of course, now that you can Google it, because we made something you can build.
Sure.
Yeah.
And now, well, thank you. And now, well, regarding a more how would I say, a new topic like that, it's now people are talking about people, physicists, not regular people, I guess, but you may have seen that, well, I actually have here the paper. We just heard from new results from dark energy spectroscopy instrument, which is DESI, which is funny because in Spanish, DESI is a name, so I find that curious. And it hints that maybe dark energy may evolve in time, you know, that it's not just like a cosmological constant, so to speak.
Yes.
So, well, I don't know if this is your area of expertise, but I just wanted your take on this. What do you think this could imply? Well, these results, as far as I know, has not been peer-reviewed yet, so we'll have to maybe be skeptic about it. But what do you think this would imply? How do you think this would change the way we see physics and the entire universe?
Well, it's unknown at the moment. If people haven't seen the results, we have various ways to estimate the rate of expansion of the universe. We have a model, which we call the standard model of cosmology, that ties everything together. And it connects the intensity and the spatial distribution of the spots in the microwave background map to the distribution of galaxies and the rate of expansion today. And even when the galaxies were first formed, all of these things should be results from a good mathematical simulation. And now we're getting answers that don't quite fit. So we have two different ways using the galaxies themselves to measure the rate of expansion, and they don't quite agree. They're using mostly supernovae as standard candles to measure the distance, and then we have the model from the cosmic microwave background spots. Those don't agree, and there are something like 6 sigma apart, which means statistically very significant.
Yeah, sure.
So there are several possible things that we could, possible explanations. One is we just made a mistake.
Yeah, sure.
That happens. One is that the universe has some features that are in the complexity of the objects we're using for standard candles. Maybe supernovae have changed over time. or maybe their light is being blocked by dust, or all kinds of things you have to check. Ways that we could be fooled by ordinary phenomena. And then there's the possibility, which seems to me quite real, that this cosmic dark energy isn't really a constant, and there's maybe more than one kind. It's even not impossible that there could be more than one kind of cosmic dark matter. How would we know? All we know is that it's there. We don't have much information about the properties of the cosmic dark matter. So I think many things are mysterious now, and we have a good challenge in front of us to try to measure better.
Sure. I mean, it's a challenge to keep physicists' families fed for a couple of years in the future,
I think,
right?
Some of these may be too difficult forever. We made, of course, as you know, we're trying to measure dark matter in laboratory experiments, and it's never been found after 50 years of searches.
Sure.
So we're working harder and harder, but it's still not there. So maybe it will never be found in the laboratory.
Sure.
So maybe we have to wait for the theoretical physicists. That idea that I wanted to pursue when I was young is to really predict something that could be tested. So far, the dark energy and the dark matter are not the result of any accepted theoretical prediction. They're just something we saw. And so it's still a great mystery. So I think we have to keep working on the theoretical physics side as well. Yeah.
That's nice, because theoretical physics is maybe not as well funded. Well, I don't know how that works in the United States, but at least here in Spain, theoretical physics, it's not really funded properly. And well, it's nice to see, well, a Nobel laureate such as yourself to
Yeah, well, theoretical physics is less expensive than experimental physics.
Well, that's for
anyway,
sure, yeah.
Because you don't have to build equipment, you just need a computer and a pencil. But it's actually quite frustrating that after all these years, we don't have a better answer. People have brilliant ideas and they just don't work out yet.
Well.
So they will. One of these days we'll have an answer, and someone will say, cosmic dark energy and cosmic dark matter should exist because of this reason. Right now we don't have that reason.
Well, we'll have to keep working.
Maybe you'll find it.
Yeah. Well, me not, but maybe some of the people in this.
Somebody that we know will do this.
That would be interesting. So, well, just to wrap up, well, thank you very much for accepting this, this interview.
Yeah.
And I just wanted to finally ask you if you maybe had some words for all the people that might be watching this and that want to pursue a career in physics or in cosmology in particular, and maybe you wanted, well, maybe they feel a little bit lost or a little bit frustrated, and if you could maybe say something to them.
Okay, well, about being lost and frustrated, it's the natural state of affairs for being a human. You're always trying to do something you never did before. It's always frustrating. But you go at it bit by bit. At first you can't walk, and then you can walk. At first you can't ride a bicycle, and then you can ride a bicycle. At first you can't swim, and then you can swim. So we're all beginners at something all the time. And so it's the natural state of affairs to be a little frustrated. So I think we should also say, and there are huge opportunities for us. This is a great time to be a scientist because we have new equipment, and they're showing us new evidence. We have international participation, international cooperation. Discoveries are being made all the time. It's a very exciting time to be alive as a scientist. And there are basically, as far as I can tell, physicists are always employed doing something. If you have you learned physics, then you've learned something very difficult to learn, and so you're now set up to learn to do anything else that's complicated and difficult because you know you can. So there are lots of areas of engineering, for instance, communications science, computer science, all those things that use the kind of training and background that physicists get. There's a lot of employment opportunities. Of course, hardly any of us will ever replace our professors because professors don't die and they don't retire. So we'll all have to look to do something else besides being a professor. But there are lots of other things to do. So I think it's a good, exciting time to be alive and to be studying science.
well, thank you very much from me and from all the COEFIS team. I think I truly believe this has been a really inspiring interview, and well, we hope we maybe get to see you again in the future, and well, that's it. Thank you very much.
Well, thank you, Daniel. Much appreciated.